Welcome to the session on solution of simultaneous nonlinear equations using Newton-Raphson method. The Newton-Raphson method we have already discussed can be extended to find the real solutions of simultaneous equations, either nonlinear, algebraic or transcendental, in several unknowns. For convenience, let me consider two equations in two unknowns. Let them be f of xy is equal to 0 and g of xy is equal to 0. Let x naught y naught be an initial approximate solution of the equations. We are taking x naught y naught as an initial approximation. Let x naught plus h comma y naught plus k be the actual solution. Then we can write f of x naught plus h comma y naught plus k is equal to 0 and g of x naught plus h comma y naught plus k is equal to 0. Expanding these two, that is f and g, using Taylor series for a function of two variables and neglecting h square, h into k and k square terms, and also we neglect the higher degree terms, then we can write f of x naught y naught plus h into dou f divided by dou x, that is the partial derivative of f with respect to x at the point x naught y naught, that is at the initial approximation, plus k into dou f divided by dou y, k into dou f divided by dou y at the point x naught y naught. This is equal to 0. That is f naught, we use the notation f naught for f of x naught comma y naught, plus h into, we use the notation fx for dou f by dou x at x naught y naught, that is 0, plus k into fy, we use the notation fy at x naught y naught means at 0, that is equal to 0. Similarly, we can write for this g by using the Taylor's theorem. We can write g naught plus h into gx, that is dou g divided by dou x at x naught y naught, plus k into dou g by dou y, that is gy at x naught y naught, which is equal to 0. Let it be equation number 1 and this be equation number 2. Solving the equations 1 and 2 to obtain h and k using the determinants, we have h is equal to, on solving these two for h and k, we can write h is equal to minus dx divided by d and k is equal to minus dy divided by d, where d means the determinant of fx naught, fy naught, gx naught and gy naught. This is d. Dx is determinant of f naught, fy naught, g naught and gy naught. This is dx, and dy is the determinant fx naught, f naught, gx naught and g naught. The values of h and k obtained are only the approximate values. Using these values of h and k, we get a better approximation for the solution as x1 is equal to x naught plus h and y1 is equal to y naught plus k. By assuming x1 y1 as initial approximation and repeating the same process, we can obtain the required solutions to the desired accuracy. Now consider an example for this method. Find the solution of the equation the given equations are simultaneous equations, which are 4x square plus 2xy plus y square is equal to 30 and 2x square plus 3xy plus y square is equal to 3. Correct to 3 places of decimals using this Newton-Raphson method. Given that x naught is equal to minus 3 and y naught is equal to 2. These are the initial approximations. X naught is minus 3 and y naught is 2. Then we want to find the solution of this simultaneous equations correct to 3 places of decimals. Here we assume f of x y as the left hand side of the first equation, that is we can write from this equation as f of x y is equal to 4x square plus 2xy plus y square minus 30. Then the given equation will become f of x y is equal to 0. And we take g of x y as 2x square plus 3xy plus y square minus 3. Therefore, fx of x comma y, that is the partial derivative of f with respect to x, that is 8x plus 2y, and the partial derivative of f with respect to y is fy, which is equal to 2x plus 2y. Similarly, gx, that is the partial derivative of g of x y with respect to x, which is 4x plus 3y, and the partial derivative of g with respect to y, that is gy, which is equal to 3x plus 2y. Now, f naught, that is f of x naught y naught. F of x naught y naught is f of minus 3 comma 2, that is putting x is equal to minus 3 and y is equal to 2 in this expression, we will obtain f of minus 3 comma 2 as minus 2. Now, g naught or g of x naught y naught, this is f naught, this is g naught. Putting x naught equal to minus 3 and y naught is equal to 2 in this expression for g of x y, g of x naught y naught means g of minus 3 comma 2, which is equal to 1. Now, f x naught. F x naught means the partial derivative of f with respect to x at x naught y naught. X naught y naught is minus 3 comma 2. This is f x. Putting x is equal to minus 3 and y is equal to 2 in this expression, we will get f x at minus 3 comma 2 as minus 20. Now, f y naught. F y naught means partial derivative of f with respect to y at the point minus 3 comma 2. Putting x is equal to minus 3 and y is equal to 2 in this expression, we will get f y minus 3 comma 2 as minus 2. Now, g x naught, that is g x at minus 3 comma 2. This is g x. Putting x is equal to minus 3 and y is equal to 2 here, we will get this as minus 6, and g y naught. G y naught means g y at minus 3 comma 2. Putting x is equal to minus 3 and y is equal to 2 here, we will get g y naught as minus 5. Now, we want to evaluate the determinants d dx and dy. D is equal to f x naught, determinant of f x naught, f y naught, g x naught and g y naught. Which is equal to determinant of f x naught is minus 20, f y naught is minus 2, g x naught is minus 6 and g y naught is minus 5. That is minus 5 into minus 20 minus minus 2 into minus 6, which is equal to 88. Value of d is 88. Now, dx, determinant of f naught, f y naught, g naught and g y naught, which is equal to determinant of f naught is minus 2, f naught is minus 2, f y naught is again minus 2, g naught is 1 and g y naught is minus 5. Value of this determinant is minus 5 into minus 2 minus 1 into minus 2, which is equal to 12. That is value of dx is 12 and dy is equal to determinant of f x naught, f naught, g x naught and g naught. That is equal to determinant of f x naught is minus 20, f naught is minus 2, g x naught is minus 6 and G naught is 1. Value of this determinant is this equal to 1 into minus 20 minus minus 6 into minus 2, which is equal to minus 32. These are the values of d, dx and dy. Therefore, h is equal to, now we calculate h. H is equal to negative of dx divided by d, which is equal to negative of the value of dx is 12 divided by value of d is 88. Minus 12 divided by 88 is minus 0.1364. Now, the value of k, we calculate value of k, which is equal to minus of dy divided by d, which is equal to minus value of dy is minus 32 divided by value of d is 88. That is minus of minus 32 divided by 8 is positive 0.3636. These are the values of h and k. Therefore, a better approximate solution can be written as x1 is equal to x naught plus h. That is x naught is minus 3 plus h is minus 0.1364, which is equal to minus 3.1364, that is minus 3.136 approximately, and y1 is equal to y naught plus k, that is y naught is 2 plus k is 0.3636, which is equal to 2.364 approximately. The better approximation are x1, y1, which are minus 3.136 and 2.364. Initially, it is given that minus 3 x naught y naught is minus 3 comma 2. We obtained the better approximation as x1 y1 equal to minus 3.136 and 2.364, which are correct to 3 places of decimals. Now, we evaluate f1. f1 means f of x1 y1. This is our f of xy, putting x1 is equal to minus 3.136 and y is equal to 2.364 in this expression. That is putting x is equal to 3.136 and y is equal to 2.364, we will get f1 as 0.0995. And g1 is equal to g of x1 y1. Putting x is equal to x1, that is x is equal to minus 3.136 and y is equal to y1, that is y is equal to 2.364 in this expression of g of xy, we will obtain g1 as 0.0170. Now, fx1. fx1 means the partial derivative of f with respect to x at x1 y1, that is fx at x1 y1. When substituting, x1 is equal to minus 3.136 and y1 is equal to 2.361 in the expression for fx, we will obtain fx1 as minus 20.360. Similarly, fy1, that is the partial derivative of f with respect to y at x1 y1. On substitution, we will get the value as minus 1.544. Now, gx1 is gx1 value of the partial derivative of g with respect to x at x1 y1, that is gx1, we will get gx1 as minus 5.452. And gy1 is partial derivative of g with respect to y at x1 y1, which is equal to minus 4.680. Now, we evaluate the determinants d equal to here d equal to fx1, fy1, gx1 and gy1. The values are minus 20.36, here minus 1.544, minus 1.544, gx1 and gy1 are minus 5.452 and minus 4.680. Value of this determinant is 86.8669. dx is determinant of f1, fy1, g1 and gy1, which are 0.0995. That is, value of f1 is 0.0995. Value of fy1 is minus 1.544 and g1, gy1 are 0.0170 and minus 4.680. Value of this determinant is minus 0.4394 and determinant dy is fx1, f1, gx1 and g1. Values are minus 20.360, 0.0995, minus 5.452 and 0.0170. Value of this determinant is 0.1964. Now, we will calculate h and k. H is equal to minus dx divided by d, that is minus of minus 0.4394 is plus 0.4394 divided by d. D is 86.8669. This is equal to 0.0051. And k is minus dy divided by d, that is minus 0.1964 divided by 86.8669, which is equal to minus 0.0023. Therefore, we can take a better approximation as x2 is equal to x1 plus h, that is minus 3.136 plus h is 0.0051, which is equal to this is approximately equal to minus 3.136 3.131 approximately, and y2 can be written as y1 plus k, that is equal to y1 is 2.364 plus k, here k is minus 0.0023, this is equal to approximately this is 2.362. These are the new approximations for xy, that is x2 y2 is minus 3.131 and y3 is y2 is 2.362. In a similar manner, we can obtain the third approximation as after 3 iterations we will obtain x3 y3 as minus 3.131 and y3 as 2.362 approximately. In the second iteration and the third iterations, we can conclude that the approximate values of x and y are approximately same. Therefore, the required solution of this system correct to 3 decimal places can be written as x is equal to minus 3.131 and y is equal to 2.362, which is the required solution. Now, let me conclude this session. In this session, we discussed the Newton-Raphson method for solving a simultaneous equations in 2 unknowns, and we have done an example for the method. Thank you for listening this class. Goodbye.